So I want to recall that last time we defined what I called an elliptic pair. If X is a rational surface, so the assumption there was some, it may assume it's smooth, but singular surfaces are also useful for computations, and so log terminal singularities is what you need to assume. And then together with an elliptic curve, which again you may assume it's smooth. In all examples, essentially, this curve is, in most examples, this is a smooth elliptic curve. But again, this is not necessary. You can take also a nodal or a cuspidal cubic. So this is a curve with self-intersection 0 and arithmetic genus 1. And then we define the order of the elliptic pair, E of Cx. This was the order of the restriction of the line bundle given by C to C. This is contained in the smooth locus of X. Yeah, so this is an honest line bundle, and with line bundle degree 0 on the curve. And we proved last time that if this order is infinite, and the Picard number of X is at least 3, then the effective cone of this rational surface is not polyhedral. But this was an argument due to Nikulin. And so, and then we also remarked that if, for example, your elliptic pair is defined over a finite field, then the order cannot be infinite. And so in that case, you cannot use this to decide polyhedrality. But so today I want to discuss also a general way of trying to approach this question about the polyhedrality of the effective cone when the order is not infinite. And also, I want to relate this to what we are after. We are after some toric surfaces, projective toric surfaces, for which when I blow up just one point, I can construct an elliptic pair with that rational surface. Yeah, so the goal was to produce blow-ups of projective toric variety blown up at one single point, a general point, such that the effective cone is not polyhedral. And we want to do this for surfaces. So how to construct now projective toric surfaces for which the blow-up at one point gives you an elliptic pair. Yeah, so for that, yeah, we are going to look at a lattice polygon. So in the plane, yeah, we want to look at polygons for which the vertices have integer coordinates. So this is what I call a lattice polygon. Yeah, so vertices are in Z2. And then I want to look at all the lattice points inside this polygon, including the vertices. And I want to consider the map from the two-dimensional torus into a projective space of dimension given by the number of lattice points in delta. So all the lattice points inside minus 1. So this is just, I take a point. So I take the Laurent polynomial. So I take monomials associated to these lattice points. Yeah, so I take all the possibilities for all the lattice points. So this is one way you can construct projective toric surfaces. Yeah, so I call P delta as the image of this map, and I take the closure. And then this comes with a very ample line bundle, namely the restriction of O1 to it. So this is now a projective toric surface, L is an ample line bundle, and you can think of the global sections of this line bundle. You can identify them with rational functions on this open torus, and these correspond to Laurent polynomials, which can be expressed as combinations of these monomials corresponding to the lattice points inside delta. Yes, and some other properties that these have. So the square of this ample line bundle is given by the twice the area. Well, this is also the normalized volume of delta. Then the number of vertices is giving you the Picard number. So the number of vertices minus 2 is the Picard number. And then, so the goal is now to find the curve in the blow up at the identity point. And so I'm going to set X to be the blow up of the identity point. And then I want to look for a curve that will make this an elliptic pair. And the most natural place to look in is this linear system given by this line bundle. So I want to look now. I want to look for curves for which. So here E is the exceptional divisor corresponding to the point that I blew up. And so I want the simplest possible curves. So the definition is really modeled in order to have this true. So I will call a good polygon is a lattice polygon. With at least 4 vertices, and such that I can find such a Laurent polynomial and such that there is such that if M is the multiplicity at the identity point, then the curve, so I take the 0 locus of this curve, close up, and I take the proper transform to X. I want this to be an irreducible curve. Such that this is an elliptic pair. Okay, which comes down now to set some combinatorial conditions. So everything will become combinatorial, except I will have to ensure that the curve I have is irreducible. So I will impose the Newton polygon of this equation is delta. So I can always look at the monomials that appear in F and consider their convex hull. And so if this does not include any of the vertices, then this curve will pass through a torus invariant point, and that's the only place where the surface may be singular. So this will ensure, this will imply that the curve is contained in a smooth locus. Then I want that the curve has zero self-intersection on the blow-up. So that means that that I want the self-intersection to be exactly m squared, the multiplicity. So that means twice the area has to be m squared, the multiplicity of f at the identity point. And then I also want that this is arithmetic genus 1. Another way to say this is that C times K is 0, the canonical class on X. And now C has multiplicity m at the identity point. Yeah, so this is just the canonical of the toric surface plus the exceptional. So C has multiplicity m at the point that I blow up, so that means I want the intersection with the anti-canonical to be exactly m. And now, yeah, so the meaning of the edges in this polygon each correspond to a torus invariant divisor, and the lattice length of that edge will be the intersection of L delta with that divisor. Yeah, so I'm saying that the condition that I write now is saying that the curve on the toric surface will intersect the sum of the boundary in M, and that's exactly the anti-canonical. And so I'm saying this will ensure that C squared is 0, and this will ensure that the anti-canonical intersects C in 0, which is what I need. Okay, and so one remark here is that such pairs are defined over the rational numbers. Yeah, so the reason is that you're looking for these coefficients of this Laurent polynomial such that the multiplicity at the identity point is m. So that's a condition on the derivatives. So some derivatives vanishing at the identity point. There's just a linear system of equations in these variables, the coefficients, and the coefficients are integer. So if there are solutions, they are defined over, the coefficients are rational. And then I will also call, such a polygon to be LangTrotter if the order of this elliptic pair is infinite. And then, so these will be the more interesting ones. And then the other situation is when the order is finite. I'll call that Hafen. These are also useful, but these are the more interesting ones because so what this will lead to, we'll give examples. So again, this will be now specific to various polygons that we analyze. So you can construct examples such that the effective cone of this blown up toric surface is not polyhedral in characteristic 0. Well, that's already, if we can construct such a polygon, we know that's true by Niculin's argument. But then you can also prove that that when you look at reductions modulo a prime, again, outside finitely many primes, this will still be an elliptic pair. And then you can prove that so these reductions also have a non-polyhedral effective cone for a set of primes of positive density. Yeah. Lang and Trotter. Trotter, yes. So I'll hope to say at the end a bit about the theorem from of LangTrotter from the 70s that allows you to prove that the second part of the statement. Yeah, so I say there is a set of primes of positive density for which the effective cone is also still not polyhedral, and then this can become interesting as again, various conjectures in number theory also will imply, for example, that this is polyhedral. In some examples, this is polyhedral also for a set of primes of positive density. And yes, and also you can also construct examples where all these cones are polyhedral in characteristic P, but not in characteristic 0, and so on. So let me just say here that so we construct many LangTrotter polygons. In fact, you can classify for M up to, so there is a database of polygons of small volume. So we looked at polygons of volume at most 49, so M at 7. And among those, then you look for this curve, and there is 184 polygons which are LangTrotter. In all the cases, the elliptic curve is smooth. It has, in many cases, the lattice length of the edges is 1. So that means that when you intersect this curve with these boundary divisors, you get rational points. And you can even construct infinite sequences of pentagons and heptagons, which are LangTrotter. So that means you have infinitely many elliptic curves defined over the rationals. You can actually prove that it is an actually infinite sequence of the J invariant is an infinite set. But we do not know that that you can bound the number of vertices. So the largest example we can construct is with 19 vertices. So that means the Picard number of this X, the maximum is 18, and there the rank of the Mordell-Weil group of rational points is 9. Okay, so this was just to say that that there are examples of elliptic pairs of infinite order arising as blobs of projective surfaces, of toric projective surfaces. Yes. Yeah.
Do you have the interpretation of the order in terms of this lattice polygon?
No. No.
So you compute it
by hand. Yes. Okay. So then, so what I didn't address is how to settle this polyhedrality question when the order is not when the order is finite. So that's what I want to discuss now. So this is, again, you can do this in general, in this generality of elliptic pairs. And this is related to classical constructions about rational elliptic surfaces, so-called Halfan surfaces, which were much studied. So again, this is in general. You can make the following. So the question is what to do, yes, if the order is finite. In this case, remember that you have a vibration given by this multiple, this is E. This multiple of this elliptic curve gives you a map to P1 with a general fiber, an elliptic curve. So general fiber here is an elliptic curve. And so what to do about, oops. Okay. So in general here, you won't be always able to settle this polyhedrality question for X, but rather you'll have to take a minimal model. So this is K plus C minimal model, and settle this polyhedrality question there. Yes, I'm going to decide if the effective cone of this minimal model is polyhedral or not. So if it is not, then also the effective cone of X is not polyhedral. But if it is, then, which can happen, it can be even that Y has Picard number 2. So in that case, we don't say anything about the effective cone of X. Okay, so the definition is that exactly I want K plus C to be an F divisor. So an elliptic pair Cx is called minimal if K plus C is an F. Yeah, so, and then equivalent conditions are that, so again, K plus C is an F. There is no curves, irreducible curves that intersect K negatively and C in 0. And then, again, equivalent condition is also that K square is 0, or that K and C are multiples of each other, rational multiples of each other. Okay, and so let me just say why this is equivalent to having K plus C in F. So saying that 2 implies 1 because if you recall, I proved last time that K plus C has exactly one section. It's effective, so you can look at an effective divisor equivalent to it. Yeah, so I have some irreducible curves. Okay, and so if K plus C intersects C in 0, and C is an F, so that means that the only way this can be negative on something is if it's one of these curves. Yeah, so all these curves will intersect C in 0. If B is a curve such that K plus C is negative on it, then it's one of these curves. Okay, and then the rest follows from the Hodge index theorem and the fact that C squared is 0, C times K is 0. So, yes, for example, K plus C has to have a negative square by the Hodge index theorem. But if you require its an F, then that's equivalent to having self-intersection 0, which comes down to K squared equals 0. Okay. Okay, so then the theorem that it's some log MMP theorem that will hold in this generality, like for surfaces, log surfaces, any characteristic, results of Fujino, for example, will give you that for any elliptic pair, you can construct a minimal model in this sense. So there is a map phi such that this is an isomorphism in the neighborhood of C. Yeah, so you only have to contract curves that are away from C. And then, so that means you can still talk about the image of C on Y. Yeah, so if I do not, I'll generally drop the subscript. Yeah, so, but then this gives you an elliptic pair on Y, which is minimal. So K plus C is now. Okay, so we can always pass at this model, and then also note that the order will not change, yes, because the phi is an isomorphism in the neighborhood of C. So when I restrict C to itself, this is the same line model. Okay, so I want now to look at this question of how to decide this polyhedrality for minimal elliptic pairs. Yeah.
That alpha is positive in your condition 4?
So for smooth surfaces,
not.
no. But in this long term, yes, it is possible.
Okay.
But so for the ones we will need, which is smooth and the surfaces with dual singularities, this is always negative.
Yeah, sure.
Yeah. Thank you. Okay. So yeah, there are rational surfaces which have plurigenera which are not zero. Okay. So some notation. Yeah, so assume now you have a. So I'll denote this by Y so that it's clear. I'm talking about a minimal pair, minimal elliptic pair. And recall that I was looking at the restriction map from C perp to big 0 of C. So divisors that intersect C in 0 will give me, by restriction, line models of degree 0 on the curve. And then this will induce a map also at the level of, if I quotient out this subgroup of the divisor class group by the subgroup generated by K. So K is 0 on C, so it lives there. This is a subgroup in the divisor class group. This is a quotient of that. Okay. And this is just the restriction of K, which is also minus the restriction of C. Okay, so I'll call this a reduced restriction map, and then this quotient, I want to call it give it the notation, so reduced divisor class group. And now I want to notice that this has now has a well-defined bilinear form coming from the intersection pairing. This is well defined because the pair is minimal. So if I add a multiple of K, it won't change this. This won't depend on that because K squared is 0. Yes. And now I want to decide. I want to look more carefully at the smooth case. Yeah, so let's look at the smooth case. Let's say, so again, I want to assume I'm going to call this Z now, just to emphasize again, this is smooth, minimal elliptic pair, Z smooth. And then I claim that that in fact indeed C is equivalent to a multiple of minus k, a positive multiple. Well, this is now immediate. You know, it's a rational multiple, but some integer n. Okay. But yeah, this is a primitive class, so it can only be multiple, rational multiple in this way. In fact, so this is now a smooth rational surface, so it is a blow-up of either P2 or Hirzebruch surface. But because we are in this, under these assumptions that minus k is nef, the only negative curves you can have here are -1 or -2 curves. And now you can argue that that you can always make some elementary transformation of your Hirzebruch surface, so that actually this is a blow-up of P2 at 9 points, which can be infinite linear. And then this is a well-studied lattice. So it's you can also easily prove it's a negative definite, even, unimodular. So and of rank 8. So it's isomorphic to the lattice E8. So the polyhedrality criterion, then it will be involving the roots of this lattice. Yeah, so the theorem, again, this is for the smooth case. Assume you have an elliptic pair which is minimal with smooth surface. Assume now that we are in the case of a finite order. So this is so at this point here, this is a Hafen surface defined as classically, yes, so a rational surface with a multiple of minus k, giving you a pencil map to P1. So then the following are equivalent. So the effective cone is polyhedral. As I said, the only negative curves you can have are -1 or -2 curves. Okay, so we're really saying that this is there are finitely many -1 and -2 curves. In fact, -2 curves is always true. There are finitely many. The question here is, are there infinitely many -1 curves? Okay, and then the criterion that is useful for us is the fact that this reduced restriction map, which is inside this lattice E8, contains 8 linearly independent roots. Oh, yeah, so there are, these are the -2 classes. So not -2 curves, but -2 classes. So self-intersection is -2, intersection with k is 0, and there are 240 roots in E8. Okay, so there is there is a similar criteria now for minimal elliptic pairs with Duval singularities. So, yeah.
So if you view Z as the blow-up of 9 points in B2,
yes.
So they lie on a cubic, and C is the transform of the cubic, I guess.
Yes, correct.
So is it something that you can tell in terms of the points on the
Yes, you can. Except you have to understand so the roots of E8, this is easy to write down. They're just an explicit list of classes, lines, conics, cubics. And then you just need to understand how, what are the points on the elliptic curve, what is the line, what are the points on it, and so everything is explicit. So 3 collinear points give you the hyperplane class. And then, yes, you can compute everything, and it has been done in different examples, also by, so, yeah, okay. It has been done also in the case when the curve is a nodal cubic, because it is of interest there also. The same picture applies there too, and yeah. Okay, so let me just mention also the Duval singularities case quickly. Yeah, so assume now that you have a minimal elliptic pair with y having Duval singularities. And again, I want to look at finite order. You can then, since y has Duval singularities, you can consider its minimal resolution. Okay, so this is also an elliptic pair because k, the canonical is just a pullback from y, so the square is still 0. This is still, it's an isomorphism in the neighborhood of C, because the C is contained in the smooth locus, so we're only blowing up singular points. So this is now still a minimal elliptic pair. So I can apply this theorem. And in fact, the polyhedrality question on Z is the same as the polyhedrality question on Y. And now you simplify a bit the problem if you work here, because there is all the -2 curves lying above the singularities of Y will give you many of these. Those will always be restrict to 0. You restrict them to C. So they will always give you classes that are in this kernel of the reduced restriction map. So it's equivalent to finding in this kernel of this reduced restriction map for Y, you want to find 8 minus R linearly independent roots, where R is this rank of the sublattice spanned by these -2 curves. R is the rank of we call the root lattice. So you take the inside this reduced inside this lattice E8. Yes, you can look at the sublattice spanned by -2 curves above the singularities of Y. Okay, so now we have all we need for deciding this polyhedrality. And so let me just sum up. And then I want to look at one explicit example. Okay, so sum up. Yes. Yeah, so if I have any elliptic pair, I can look at its minimal model. And so again, if the order was infinite to start with, then I know the effective cone is not polyhedral by Nicolin's criterion, so I can stop. And then if it's finite, then I need to, okay, I do want to make one remark here, sorry. So in this case, there is one more thing that is very useful that you can say. So in this case, actually, you can prove that on the minimal model, k plus k plus c is actually equivalent to 0. So in fact, you contract all the curves that appear in when you write k plus c as an effective combination of curves. You need to contract all these curves. So this comes from the fact that when you restrict to c, this has infinite order. So the only possible way to have this is like this. So this is all on y. And this is also useful because now on y has log terminal singularities, but if this holds, that means that the canonical is a Cartier divisor, because C is a Cartier divisor. So in fact, y has to have Duval singularities. Okay, all right. So then, yeah, so the second case was if the order was finite. In that case, we have a polyhedrality criterion for y. The one, if y has Duval singularities. Okay. Okay. And so let me just say that for us, we want to apply this for a toric elliptic pair. So one of these elliptic pairs arising from blow-ups of toric surfaces. And so our situation is that you have an elliptic pair defined over the rational numbers. And let's say delta LangTrotter. So that means the order is infinite. So then we can still take the minimal model. And then I can take, as I said, in this case, this has Duval singularities. And I can consider its minimal resolution. So this is in characteristic 0, but outside of finitely many primes, I can reduce modulo p and have the same picture. So maybe, possibly outside, I have to discard some primes where something changes in the geometry of what's going on here, but I want to do exactly the same thing. Yeah? So contract all the curves that appear as components when I write k plus c as an effective divisor, I want to contract them. And I don't want any new curves appearing okay, so the picture would be exactly the same for p primes, but yeah, possibly I discard finitely many. And so I need to decide what's happening here with the effective cone of y. And so that's equivalent to this question here. So I call this to be a polyhedral prime if the effective cone is polyhedral and non-polyhedral otherwise. And now there the question becomes, you have this lattice, this E8 lattice, and this reduced restriction map. If you want, this is on ZP, and you're looking now at the FP points of this elliptic curve, and you mod out by the subgroup generated by the point given by the restriction of the canonical. So A is the restriction here. A is a restriction of the canonical. Yeah, so this is a rational point on the curve. Okay, so now I want to show you some slides in the last 2 minutes. Okay. Okay. Sorry. Okay. Okay, so I can also do this. Yes. Okay. Yeah. So just take 2 minutes. Yeah, so this is like a concrete example. Yeah, so here m is 6. So I have a polygon with area twice the area is 36. There are 6 lattice points, just the vertices. Each edge is lattice length 1. There are no other lattice points on it. Then you can compute using magma that this linear system of Laurent polynomials with multiplicity 6 at the identity point contains just one. It's one-dimensional. So there's only one curve with this property that has multiplicity 6 at the identity points, and it has Newton polygon exactly this polygon delta. Yeah, so the monomials in red are exactly corresponding to the vertices of this polygon. Then again, it's a magma algorithm to compute a minimal Weierstrass equation. And it turns out this is actually a smooth elliptic curve. And in the database of elliptic curves, this has this label, and that gives you a lot of information, such as, so the Mordell-Weil group is free of rank 2. It has 2 generators given by these 2 points. Now you can compute the restriction of C to itself, and it's minus the point Q that I wrote there. So this is not a torsion point. So this is a LangTrotter polygon according to our definition. So these restrictions you can, you can compute the restriction of every torus invariant divisor to the curve, and the class of the curve can be expressed in terms of those. So you can also do some of these calculations by hand up to a certain point, but so my collaborators are very proficient in Magma, and they implemented everything in Magma. You can compute everything, all the restrictions, all the points on the curve. So now let's look at the blow up at the identity point. There you need to look at this divisor, effective divisor with one section. You can also compute this by Magma, the equations of these curves. There are 2 curves that appear there with coefficient 3 and 2. You can also describe them as some proper transform of some one-parameter subgroups. And so to get the minimal elliptic pair, you need to contract both these curves. So you can do this again in many different ways. So you can also just blow up, take a minimal resolution of your toric surface, blow up the identity point, and then reach the minimal model there. And that turns out to be exactly the minimal resolution of this Y, which has the Duval singularities. So Picard numbers here are, so X has Picard number 5, Y has Picard number 3. The minimal resolution is always of Picard number 10. It's a blow up of P2 at 9 points. The minimal resolution contains 10 more rays. So this is a picture, you just add, this is a minimal resolution, you add the rays which are not in bold. And then among these rays that you added and the 2 curves C1 and C2 that appear that we need to contract, you can also compute how they intersect. And you can now reach this Z by contracting here the -1 curves that you see, and that appear after contracting a -1 curve. And so you can see this here. In the end, you can contract everything up to a chain of 7 -2 curves. So you can, okay, so, yeah, so again, we need now to decide if this reduced restriction map and how many linearly independent roots it contains. And then this sublat is spent by the class of -2 curves above the singularities. We see also from that picture that this is the A7 lattice embedded in E8. And now you can compute again there is only one way to embed this A7 lattice in E8. And so you can also compute this way that, so it helps to have this many -2 curves that we know they restrict to 0. So that means in the end we are left to decide just if in this quotient of E8 by A7, which is rank 1, what are the images of the roots and how do they restrict? So these roots are multiples of this of a generator, 1, 2, or 3. And then the restriction of this generator is also computed in terms of the two generators of the Mordell-Weil group. So now to decide polyhedrality in characteristic P is to decide if these multiples, these multiples of these points, Q points, when you restrict the modulo P, if these multiples of the point P belong to the subgroup generated by the point Q, modulo P. Okay, so there is a magma algorithm that does this, so you can compute everything. Yeah, so the one there is just the fact that there is only one curve in this linear system. You can compute the root lattice, the images of the roots, and then get the primes which are non-polyhedral up to 2000. But there is also, you can do this, so if you want to prove that the non-polyhedral primes have positive density, you need a different way. And so, for example, it suffices to prove that if you have a prime, let's say Q, another prime, that the set of primes such that this Q divides the index of the subgroup generated by Q, but does not divide the index of the subgroup generated by 6 times the point P. So you want to look at such primes to prove that this has positive density. Yeah, so this would prove that none of these multiples can be contained in the subgroup generated by the point Q. And so this is so this is where the LangTrotter theorem comes in. So the LangTrotter theorem is a criterion in terms of some Frobenius elements at P of certain Galois extensions that gives you exactly the condition that Q divides the index of a subgroup. And then there's a Chebotarev density theorem, which says that if you have a Galois extension and you look at the conjugacy class, which is a non-empty, then the set of primes where these Frobenius elements belong to this conjugacy class has positive density. So I think I'm over time, so I'm going to stop there.
Questions or comments? No? Or maybe I have a question. How do you go back to the moduli space of
Okay. Okay. So, sorry. Okay. Okay. So this is the example. Yes. So there is another polygon, which is not the one I explained, but this is just has 7. The multiplicity is 7, and now when you project so you take the normal fan of that, and there is a way to project from the rays of the Lossemann space of dimension 7. There is a way to set some of the rays equal to 0, such that when you project, you arrive at this, the black dots. Those are the images of all the rays of the Lossemann space, LM10. And then the red dots are among those black, and those are correspond to the normal fan of our polygon. And so the fact that this is a subset of that means that, so I know now that this projective surface corresponding to the red dots, when blown up at the identity point, has a non-polyhedral effective cone, then a subdivision of this polygon, yes, will give me another surface that has the same property. And now I use this result of reconstructing toric surfaces which admit rational contractions, or whose blow-ups admit rational contractions to the blow-up of this surface. And there is this result that I said, if a rational contraction will preserve the property of being having a polyhedral effective cone.
Rational contraction will preserve
The property of having a polyhedral effective cone. So if I have a rational contraction, from X to
Yes,
Y. This is a
yes.
rational map, which is a composition of surjective morphisms and small modifications. So if the effective cone of X is polyhedral, then the effective cone of Y is polyhedral. If the effective cone of Y is not polyhedral, which is this surface now, that means the blow up of the Losse-Mani space of LM10 blown up at the identity is also not polyhedral.
Okay. Thank you. Other questions or comments? If not, then we thank Anna Maria.